Good morning, dear students. Today we are going to discuss topic sampling theorem, which is in the unit 5th in cybersecurity subject, cybersecurity branch. So let us understand what is sampling. Sampling is defined as the process of measuring the instantaneous value of continuous time signal in a discrete form. Sample is a piece of data taken from the whole data which is continuous in the time domain. When a source generates an analog signal, and if that has to be discretized having ones and zeros, that is high or low, the signal has to be discretized in time. This discretization of analog signal is called as sampling. The following figure indicates a continuous time signal xt and a sample signal x of st. When xt is multiplied by a periodic impulse train, the sample signal x st is obtained. So from the figure it is clear that xt is a continuous time signal and sample signal is xst, which is discrete in nature. Sampling rate. To discretize the signals, the gap between the samples should be fixed. That gap can be termed as a sampling period Ts. Sampling frequency is inversely proportional to the sampling time, that is 1 by Ts, which is equal to Fs, where Ts is the sampling time and Fs is the sampling frequency or the sampling rate. Sampling frequency is the reciprocal of the sampling period. The sampling frequency can be simply called as sampling rate. The sampling rate denotes the number of samples taken per second or for a finite set of values. For an analog signal to be reconstructed from the discrete signal, sampling rate should be highly considered. The rate of sampling should be such that the data in the message signal should neither be lost nor it should get overlapped. Hence, a rate was fixed for this. It is called as the Nyquist rate. Now, Nyquist rate. Let us understand what is Nyquist rate. Suppose that a signal is band limited with no frequency components higher than the W hertz. That means W is the highest frequency. For such a signal, for effective reproduction of the original signal, the sampling rate should be twice the highest frequency, which means Fs is equal to 2W, where Fs is the sampling rate, W is the highest frequency. This rate of sampling is called as Nyquist rate. A theorem called sampling theorem was stated on the theory of this Nyquist rate. Now, sampling theorem. The sampling theorem, which is also called as Nyquist theorem, delivers the theory of sufficient sample rate in terms of bandwidth for the class of functions that are band limited. The sampling theorem states that a signal can be exactly reproduced if it is sampled at the rate fs, which is greater than twice the maximum frequency w. To understand this sampling theorem, let us consider a band-limited signal, that is, a signal whose value is non-zero between some W and W hertz. Such a signal is represented as xf equal to 0 for f is greater than W. For the continuous time signal xt, the band-limited signal in frequency domain can be represented as shown in the figure. So it is a band-limited signal between minus W and W. We need a sampling frequency, a frequency at which there should be no loss of information even after sampling. For this, we have the Nyquist rate that the sampling frequency should be 2 times the maximum frequency. It is the critical rate of sampling. If the signal xt is sampled above the Nyquist rate, the original signal can be recovered, and if it is sampled below the Nyquist rate, the signal cannot be recovered. The following figure explains a signal if sampled at a higher rate than the 2W in the frequency domain. Here XSW is a sampled signal in a range of minus W naught to plus W naught. The above figure shows the Fourier transform of the signal X of ST. Here the information is reproduced without any loss. There is no mixing up and hence recovery is possible. The Fourier transform of the signal XST is XS omega equal to 1 upon Ts sigma n range from minus infinity to infinity xw minus n omega naught, where ts is the sampling period and omega naught is 2 pi upon ts. Omega naught is the angular frequency. Let us see what happens if the sampling rate is equal to twice the highest frequency, 2W. That means Fs equal to 2W, where Fs is the sampling frequency, W is the highest frequency. Excess of omega is a sample signal. The result will be shown as in the above figure. The information is placed without any loss. Hence, this is also a good sampling rate. Now let us look at a condition. The resultant pattern will look like the following figure. We can observe from the above pattern that the overlapping of this information is done, which leads to mixing and loss of information. This unwanted phenomena of overlapping is called the aliasing. Aliasing. Aliasing can be referred to as the phenomena of a high frequency component in the spectrum of a signal taking on the identity of a low frequency component in the spectrum of its sampled version. The corrective measures taken to reduce the effect of aliasing are: in the transmitter section of PCM, a low pass anti aliasing filter is employed before the sampler to eliminate the high frequency components which are unwanted. The signal which is sampled after filtering is sampled at a rate slightly higher than the Nyquist rate. This choice of having the sampling rate higher than the Nyquist rate also helps in the easier design of the reconstruction filter at the receiver. Thank you. We will meet in the next session.